right, hello and welcome. Here we are, another question. This is going to be find elements in a contaminated binary tree, question number 1261 on LeetCode. Let me give you a moment here to make sure that the audio is working. Find elements in a contaminated. And now I'm going to pop my chat out and we'll begin in a moment. Let's make sure these things are working correctly with timestamps. Okay, yes, so let's do it. Okay, find elements in a contaminated binary tree. All right, given a binary tree with the following rules. Root.value is 0 if tree node.value is x and tree node.left is not equal to null, then tree node.left.value is equal to 2 times x plus 1. If tree node.value equals x and tree node.right is not equal to null, then tree node.right.value is equal to 2 times x plus 2. Okay, so we start at 0. The left side is going to be 1, the right side is going to be 2. And then on the left side, from 1, it's going to be left side is going to be 3, the right side is going to be 4. And then from 2, the left side is going to be 5, and the right side is going to be 6. Yeah, okay. Now the binary tree is contaminated, which means all tree node.val have been changed to -1. Implement the find elements class. Find elements tree node.root initializes the object with a contaminated binary tree and recovers it. Bool find int target returns true if the target value exists in the recovered binary tree. So -1, recover 2, 0, 2. Okay, that's interesting. I'm not sure exactly what to say about this. All right. I think I know what to do. Find 1 false, find 2 is true, find elements -1, -1. Okay, pretty low submission rate, but pretty high acceptance rate. I think I know what to do here, but it's a little bit awkward, quite frankly. Height of the binary tree is no less than or equal to 20. The total number of nodes is between 1 and 10,000. Total calls of find is between 1 and 10,000. Target could be 0 and 10 to the 6th. I mean, a really straightforward way of doing this is to use I think probably the best way that I would go for is to use, the way that I would do it is just use a hash set. Use a hash set for the numbers. Again, the height is at most 20, so the numbers themselves are, they're not going to be too large. Only about 1 million. Yeah. A few million. Yeah, I think using a hash set is probably the easiest way to go. Recover all in one shot. Recover, one depth first search. Recover all the numbers that are there, and then just put those into a hash set. And then the find, you just check the values in the hash set. That's probably the easiest way to do this. This is like kind of straightforward if you do it that way. So that would be like the following. Let's do private. Let's do hash set of integers, vals, and we're going to say, let's actually do a DFS down here. This is probably, I can actually do it, so we'll do it this way. I was going to say, normally I would make a lambda expression, but actually this is a private member, so I don't need to make a lambda expression. So we're going to say, if not node, return, otherwise DFS on node left and node right. And we're going to say value this is current value. We're going to say vals.insert current value. And these are going to be 2 plus 1, which could actually just be written as such. If the depth, yeah, it's not going to be more than like a couple million, so it should be fine. The depth is relatively small, so yeah, that's fine. So when we find elements, we're just going to DFS on the root with a 0, and then just return vals.find is not equal to vals.end. That's kind of it, I think. That's all you really need. Yeah. I'm gonna go for it. Just gonna do it. I don't know if this is right or not. I didn't test it, didn't think about it very much. Oh, got it. Okay. Maybe that's why people skipped it. That was pretty straightforward. That's not that hard. I don't know what to say about that. That's amortized linear in the number of nodes, or yeah, something like that. I mean, not amortized. Yeah, it's like amortized linear. Yeah. Oh, not amortized linear. I mean, it's defined routines should be amortized constant, and there's at most whatever 10,000 of them, and then the number of nodes is at most 10,000. So it's basically amortized constant time. Assuming you actually run 10,000 calls. Otherwise, this may be not the most efficient way to do it, but in the worst case, this is pretty efficient. In other cases where like you're not running that many find routines, this is maybe not the best way to do it, but I don't really know if there's a much better way to do it actually, even in those cases, because you still have to go through like most of the tree to even find out which nodes you have or don't have. So yeah, it looks like this is very dependent, the speed on like just, I guess, how it's being run. Sometimes it's pretty fast, sometimes it's not. 98% is reasonable. All right, we'll stop there. So yeah, thank you for watching. If you liked that video, give it a like and subscribe for more. I'm gonna restart the stream on another question.